It's a long way from Goettingen to the Zugspitze and back. Here we are at the Max Planck Institute for Dynamics and Self-Organization. Our institute was founded in 1924 by Ludwig Prandtl, who also worked on fluid dynamics, and by coincidence we are doing now the same similar things that he was doing already a long time ago. Behind me you see our wind tunnel. This wind tunnel we can pressurize to about 15 to 20 bars, and the kinetic energy in the gas is very high, and so we can produce very high turbulence levels, but at relatively low speeds. To get these very, very high turbulence levels, we have to play some tricks. What we do is we use an active grid, which consists of flaps that are moving in the wind. And by this motion of these flats, we can produce vortices and disturbances, which then propagate down the tunnel and produce wonderful turbulence, just like in the atmosphere. Of course, this was machined, like a lot of things here in our whole institute are machined by our exquisite machine shop. As you have seen in the experimental hall, we have an active grid to produce the very high turbulence levels. What you saw there is the prototype that we now tested, and we are satisfied with the prototype. And so what we have now developed is the final product. To do so, you have to machine, for example, all the different flaps for the tunnel, which are now slightly modified from before. Here you see that you need many of them. You need about 130 of them. And by putting such a grid into our wind tunnel, we can produce turbulence levels similar to that of the atmosphere. And then what we can do is, because our tunnel is relatively slow, our tunnel only is actually flowing at 5 meters per second. What we can do is we can take a sled, or in other words, a little car, a cart, and on the cart we can mount high-speed video cameras, and then we can drive with the wind and follow little particles flying in that wind. And we heard about that at the Zugspitze there's this enormous opportunity to do experiments there, and then we decided to build a device that we can fly up with a helicopter, which we can align with the wind direction. That's why it looks like a seesaw. And then where we can drive with the wind. We can use exactly the same technology we're using here in the tunnel. It's a little more tricky because, well, here in the tunnel we have high pressure with the saw. On the Zugspitze we have water vapor and moisture and cold temperatures and sunshine and all the nastiness of nature. The experiment altogether weighs 6.5 tons. Now what we have to do is we have to mount on the sled, we have to mount our video cameras in a hermetically sealed box, which is completely environmentally isolated, and then we illuminate that with about 40 watts of laser light, and then we can follow each individual cloud droplet that's moving while we are driving with the sled with the cloud. The whole thing started here in Goettingen, and the experiment that is now standing on the Zugspitze has been designed over the period of 4 years totally. So the first 2 years we built the prototype, we tested the prototype, and then after another 2 years we finally had the real product. Every part was here designed, including which screw hole is where, which screw is where, and you can see this here in the technical drawing. So this is the actual drawing of the machine, and we can even move the part back and forth on the machine. You can even see where the video camera will be mounted. They will be in this blue box that you see here in the movie. It will be where our 4 high-speed video cameras are.
So this is the first prototype that we have built. This is the prototype that was built first before we tested the new design, and now we're testing again the design for the tunnel. So starting from April next year, I will be spending a lot of time at Zugspitze, weeks and weeks, first testing that everything's ready and then doing the actual measurements, because we have to get as much done during the summer when we have the right kind of clouds there. Well, I'm a big fan of mountains, so this is a project that I really like. But yeah, it's a much bigger project than I anticipated when I first started, because it involves so many people, but it's also an important project, and yeah, it's great to be a part of it.
Of course, it's very hard to follow the wind and to do particle tracking while you're following the wind, because you only have this 1 second of measurement time, and then you have to drive back your sled, and then you run it again. You have to read out your video cameras, which is a lot of data. And so it's of course nicer to have a stationary flow where basically the wind, the turbulence is there, but it doesn't move. And so this we make in the crystal ball.
So what we're doing here is producing conditions very close to like in the atmosphere. We're producing a cloud of small water droplets, which are getting mixed by a turbulent airflow, which is produced by these loudspeakers. So we have a whole bunch of loudspeakers here over the surface of a plastic sphere, and inside the sphere we have air with a cloud of small water droplets, which is getting mixed up, and we're watching the droplets with these high-speed cameras. So these high-speed cameras are focused on a very small region in the middle of the ball, so we can see the motions of the individual droplets and the relative motions between those droplets, and we can see whether the droplets collide and under what conditions they collide and how fast they collide and whether they produce bigger droplets and ultimately whether they produce rain.
So far I have been talking about looking at very small regions of a cloud, like a few cubic centimeters. Now I would like to look at a whole range, a whole region of the cloud to see how are droplets distributed in the cloud. One trick to do that is you use a light sheet. Now a light sheet is very easily generated. You take a laser beam, you run the laser beam on a glass fiber, and then suddenly this is a cylindrical lens, you get a light sheet. So you have this huge light sheet of light, and then in that light, of course, what you get is the light is scattered, and the droplets scatter the light. So where there's no droplets, you do not see any light reflected, and so you see beautifully the inhomogeneity of a cloud. So what we have to do is we have to get from this condensation of small droplets to larger droplets, and then we would like to understand at the end of the day, if you look at a large scale, how are these cloud patterns distributed? How do they look? Now there's one way to do this in the laboratory, in a very small experiment where we take the large atmosphere and we make it small so that it's only 2 centimeters high, 4 centimeters on the side, it's square, so it's a little square box. And in this little square box, we make an artificial cloud and study how condensation works, how cloud patterns work, how does this all impact the dynamics of this convective flow, because most clouds that we study are actually convective. From all these experiments, all my scientists and my technicians, we all hope that within a few years we have created some mathematical modeling, some real understanding of cloud dynamics, which then will allow to predict the climate in a better way. At the same time, we hope to improve the weather forecast. So in other days, we would like to say that surely this day, even there's clouds, there will be no rain.